A regular polygon has 7 sides. Find the measure of one interior angle and the measure of one exterior angle. So let's think about what kind of qualities this 7-sided figure, this heptagon, must have because it is regular. One of the properties it has is it has rotational symmetry. So since it's a 7-sided regular polygon, it has 7-fold rotational symmetry. Another property that this polygon has, because it's regular, is that all of the sides are congruent. But the property that's going to be the most helpful here is that all the angles are congruent. So we want to find the sum of all the interior angles. And we can do that by subdividing the interior into triangles, which we know each have an angle sum of 180 degrees. Since it's a 7-sided polygon, we have 5 triangles that we've subdivided the interior into. And each of those 5 triangles has an angle sum of 180 degrees. So the total of the interior angles inside this regular polygon would be 5 times 180 or 900 degrees. But we want the measure of one angle. Since all 7 angles are congruent, and that's because this is a regular polygon, we can take that 900 degrees and divide it into 7 equal parts, and we'll see that each interior angle has to measure 128 and 4/7 degrees. Now for the exterior angles, we need to remember that for any polygon, the sum of all the exterior angles is 360 degrees. And since this is a regular polygon, all 7 exterior angles are congruent, so the measure of one exterior angle is 360 divided by 7, or 51 and 3/7 degrees. Find the measure of the missing angle. Now this isn't a regular polygon, but we can still find the sum of the measures of all of the angles. Since this is a 6-sided polygon, it's a hexagon, the sum of all the angles inside the polygon is 4 times 180, or 720 degrees. Now so far, the sum of all the angles that we know is 540 degrees. We get that simply by adding all the angle measures together, which means the missing angle has to be 720 minus 570 degrees, or 150 degrees. Find the area and the circumference of a circle with a diameter of 12 inches. To find the area, we can take pi times the square of the radius. The radius of this circle is 6 inches because the diameter is 12. So we need pi times 6 squared, or 36 pi square inches. For circumference, we can say that the circumference is pi times the diameter, which is 12 pi inches. Find the radius of a circle with circumference 10 pi inches. We know that the circumference of a circle is 2 pi times the radius. And we know that the circumference of this circle is 10 pi. So 10 pi has to equal 2 pi times the radius. If we divide both sides of the equation by pi, and then divide both sides of the equation by 2, we'll get that the radius is 5 inches. Find the area of the sector. So the first thing we would need to do is find the area of the entire circle, which is pi times its radius squared, or pi times 4 squared. And then we need to multiply that entire area by a fraction which tells us what fractional part of the circle we have in the sector, which is 75 out of the 360 degrees in the entire circle. If we simplify, we'll have the area equals 10/3 pi square centimeters. The key on a basketball court is in the shape of a rectangle surmounted by a semicircle. Find the area and the perimeter of the key. For the area, we'll need the area of the semicircle plus the area of the rectangle. Now the semicircle has a diameter that's 12 feet. So the semicircle's radius would be 6 feet. And for the rectangle, we simply need its length times its width. So that gives us 1/2 times pi times the radius squared. The 1/2 is because we have a semicircle, not a full circle, plus 12 times 19 for the area of the rectangle, which gives us 18 pi plus 228 square feet. For the perimeter, we need the circumference of half the circle, plus we need the length of the 3 sides of the rectangle that we have. So we need 1/2 times 2 pi r being our circumference formula for a circle, plus we have 1 length and 2 widths. We're only counting the sides of the rectangle that are on the outside for the perimeter. So the radius of the circle, remember, is still 6. And for the perimeter of the rectangle, or at least 3 sides of the rectangle, we have 2 sides that are 19 and 1 side that's 12. So our perimeter is 6 pi plus 50 feet. Find the area of the regular pentagon, and then find the area of a similar pentagon, which is an enlargement of this pentagon by a scale factor of 3. So the trick here is to see a triangle within that pentagon, because we know how to find the area of a triangle. It's 1/2 times its base times its height. So the area of this triangle would be 1/2 times 16 times 15. But within the pentagon, we have 5 identical triangles because it's a regular pentagon. So the total area of the pentagon is 5 times 1/2 times 16 times 15, or 600 square inches. Now for the scaled pentagon, remember that if we have a scale factor of 3, meaning we have a pentagon that has sides that are 3 times as long, that will make the area 9 times as large, 3 squared times as large. So the area of our scaled pentagon is 5,400 square inches. The inner ring of this figure has a diameter of 4 units, and the outer ring has a diameter of 12 units. What is the area of the figure between the 2 rings? So what we need to find here is the area of the larger circle minus the area of the smaller circle on the inside. It's almost like we're looking at a donut here. We have a hole that's cut out of the middle. Now the large circle has a large radius, an outer radius, and the smaller circle has its own radius. So we'll need to find the radius of each of these parts. But what we've been given is diameter. So the large circle has a diameter of 12 units, which means it has a radius of 6 units. And the small circle has a diameter of 4 units, which means its radius is 2 units. So we need to find pi times 6 squared minus pi times 2 squared, which is 32 pi square units of area. What is a regular tiling? A regular tiling is made up of only one kind of regular polygon. So which regular polygons could be used to make a regular tiling? There are only 3 regular polygons that can be used to make a regular tiling. They're the square, the equilateral triangle, and the regular hexagon. What is a semi-regular tiling? That's a tiling made up of more than one kind of regular polygon. Here's a few examples of semi-regular tilings. You'll see that in each case we have a tiling that's made up of more than one polygon, but the polygons are regular polygons. What is a uniform tiling? That's a tiling that contains multiples of just one kind of vertex. Here's an example of a uniform tiling. Now, if we have a uniform tiling, we can also identify the vertex net. So what's the vertex net for this tiling? So to find the vertex net, find any vertex and then look at the polygons that surround that vertex. So I'm going to start with this polygon. That's a hexagon. It has 6 sides, and I'm just going to move around clockwise. So I have a square with 4 sides, then a triangle with 3 sides, and then a square with 4 sides. So the vertex net would be 6, 4, 3, 4. What is a periodic tiling? That's a tiling in which a translation of a portion of the tiling will cause it to match another portion. Here's an example of a periodic tiling. This is one of Escher's works. We can find part of this tiling that we could repeat over and over and over again to make the rest of the pattern in the tiling. Now, if we have a periodic tiling, we can also make a lattice, and in that lattice we can find a fundamental region which we could repeat over and over and over again in order to complete the tiling. What is a Penrose tiling? A Penrose tiling is a non-periodic tiling that consists of shapes called kites and darts, or shapes called diamonds and rhombi. This particular example is a Penrose tiling that is made up of kites and darts. And what's important about the kites and the darts is that the proportions that make up those two shapes are based on the golden ratio. Find the value of x. So what's important in this particular circle is that we have an arc that is subtended by 2 angles. The 140-degree angle has a vertex at the center of the circle, and the other angle that measures x degrees has a vertex that's on the circle. Because of that, we know that the 140-degree angle has to be twice the measure of the angle that's labeled x, which means x has to be a 70-degree angle. Find the value of theta. Now we're going to have to look at several angles to find theta. First of all, we have two angles that are supplementary. So we know that this angle has to be a 40-degree angle. We also have a triangle, and there's one angle that we don't have identified in that triangle, but we know all three angles have to add up to 180 degrees, which means this angle in the triangle has to be 96 degrees. So now the final thing we need to notice is that we have an arc that is subtended by two angles. One of those angles is the 96-degree angle, and its vertex is on the circle. And the other angle is the angle marked theta, and its vertex is also on the circle. So since both of those angles subtend the same arc, and they both have a vertex on the circle, their angle measures have to be the same. So theta has to be a 96-degree angle as well. Ray PA is tangent to the circle at A, and ray PB is tangent to the circle at B. Find the measure of angle APC. The first thing that we need to look at is that 59-degree angle. We know that this angle, angle ACP, is also a 59-degree angle. That's because ray PA and ray PB are both tangents, so segment PC has to bisect angle ACB. The next thing we can notice is that since we have two tangents to the circle, those tangents have to be at right angles to each of those line segments that makes up the radius between the point of tangency and the center. So now we've got a triangle that has a 90-degree angle and a 59-degree angle. So the remaining angle has to be a 31-degree angle because the sum of the angles in the triangle has to be 180 degrees. And that's the angle we're looking for in this particular case. So angle APC is 31 degrees. Find the value of x. Because we have two chords on this circle that intersect, we can multiply the lengths of the pieces of the chords, and we know that those products will be the same. In other words, 5 times x will have to equal 11 times 4. Which means that x has to be 44/5 or 8 4/5 units long. Use the polygon to draw a 5-2 polygram. So to begin the polygram, we need a starting point. So we'll pick a vertex, and because it's a 5-2 polygram, the 2 means we're going to count 2 vertices from that starting point in either direction. So 1, 2, and we'll draw our first line segment from our starting point to the vertex labeled 2. And then we'll continue this process. We'll count 1, 2, and draw a line segment. We'll count 1, 2, and draw a line segment. And we'll keep doing that all the way around until we either get back to where we started, which is what's going to happen here, or If we get back to where we started and we still have vertices remaining, we will move to one of the remaining vertices and start the process all over again. Use a compass and straightedge to construct a regular hexagon. So, to construct a regular hexagon, we're going to start with a circle, and then keeping the compass at the same setting that we used to draw the circle, we'll draw 6 arcs around the circle, using those intersections that we draw as the point that we start drawing our next arc with. Then all we have to do is use a straightedge to connect the lines, or connect those intersections up with line segments, and we'll have a regular hexagon. Use a compass and straightedge to construct a tangent to the circle at point P. So we're going to use the fact that a tangent to this circle has to be perpendicular to the radius that goes from the center to P. So we could start by drawing a line segment that passes through O and P, and then we're just constructing a perpendicular to that line segment that goes through point P. That perpendicular is tangent to the circle at point P. Construct the perpendicular bisectors of the 2 chords shown in this circle. Label the point of intersection of the 2 bisectors E. What's important about point E? So we have the same construction to do twice. We'll have to construct a perpendicular bisector for one segment and then repeat that for the other segment. So first we'll construct the perpendicular bisector of the shorter segment in this case, and then construct a perpendicular bisector of the longer segment. And we'll extend those until they meet. The point of intersection is the center of the circle. So if we label that center E, then what's important about point E is that it's the center of the circle.